Okay, hi everyone. Thank you for joining us today on the Embodied AI lecture series. Today we are honored to host Chelsea Finn. She's an assistant professor in computer science and electrical engineering at Stanford University. And she's interested in capability of robots and other agents to develop broadly intelligent behavior through learning and interactions. She's also affiliated with Google Brain, and she's won plenty of awards, including MIT Technology Review 35 under 35. And we are very pleased to host her today. Her work has been very impactful in the domain of embodied AI. And we would love to hear about her recent works and line of research. Thank you for inviting our invitation, Chelsea, and take it away.
Awesome. Yeah. Excited to virtually be here. There should be plenty of time for questions, so feel free to interrupt in the middle by raising your hand or just like unmuting and speaking up. I'll be talking about some of our work on trying to allow robots to reduce, reuse, and recycle. So to start off, in terms of I think it's useful to look at like where we are today, what robots can do today. And in particular, these are two videos. The left video shown here is a project actually now 6 years ago that I was working on, where we were trying to allow a robot to learn a manipulation skill using neural networks. And we see that the robot actually seems pretty capable here. It's able to use a spatula in a fairly smooth way to lift up an object and place it into a bowl. And this seems actually pretty nice, pretty impressive. And likewise, on the right here, here's a video from Boston Dynamics. And the robot is doing completing a fairly impressive kind of obstacle course of some kind and doing these acrobatics. And I think that in general, if you were to look at these two videos, you would think that robots are probably pretty capable these days. They can do things that look pretty impressive. But I think the catch here is that first, on the right, this video was behavior that was manually tuned for this particular environment. And so if you change something about the environment, maybe you change the position of some of the blocks, for example, you'd have to kind of tune it again manually for that new environment. And likewise, for this behavior on the left, it was trained from scratch using 15 minutes of data in that environment. And that means that if you gave the robot a different spatula, or maybe you move the position of the bowl a little bit, or the position of the initial position of the object, in that case, the robot wouldn't actually be able to succeed in those scenarios. And you'd have to then maybe train it again from scratch. And so the issue here is that, the good thing is that we know robots can perform pretty complex maneuvers, and we can train them to do that. But those complex maneuvers are specific to narrow and controlled environments. And so since, I guess in the past 5 years, since we were working on the video on the left, I've been really interested in how we might actually start to get robots that can act in much broader settings and actually be successful, not just in one particular scenario, but in lots of different scenarios. So in particular, how we might allow robots to go out of the lab and generalize in the wild. Now, I don't have the answers to how exactly we can do this, but one recipe that's been arguably extremely successful in other areas is to combine large expressive models with broad data sets. And I'd say arguably this is really one of the only recipes that is convincingly enabled in the wild generalization for applications such as speech recognition, natural language processing, and computer vision. Now, we know how to build a large network and throw out a problem, but the challenge is the question, where does the data come from? So in robotics, unlike in NLP or in computer vision, there isn't massive amounts of data just sitting on the internet that we can use. And it's not exactly trivial to collect data for these kinds of scenarios. Now, in terms of thinking about this question, I think it's useful to kind of look at where the data typically comes from in reinforcement learning and embodied learning settings, and contrast that with where the data typically comes from in other machine learning settings. And so in the robot learning research community, typically the data is collected for a specific project. This doesn't seem necessarily like a bad thing until you realize that then we don't use the data again, and we collect new data for each and every project. And if we want a system that can generalize very broadly, it's going to be pretty expensive to collect the data set from scratch every single time. And in contrast, what the machine learning research community does is to collect a large data set, to collect it once. Maybe we collect a few of these data sets like ImageNet, Wikitext, and so forth. And we reuse it many, many times. We don't just throw it away once, we reuse it. And in fact, actually, we don't even do that. We actually often do something even better, which is we don't reuse the data set directly, we reuse a pre-trained model that was pre-trained on that data set. And so I think that if we hope to get the kind of generalization that we see in a lot of machine learning research, maybe we should do what machine learning research often does from a data standpoint. And so I would argue that robots should reduce, reuse, and recycle. They should reduce their reliance on special purpose data collection, reuse previously collected data, and recycle pre-trained models, just like the rest of machine learning. Cool. So we certainly haven't solved this completely. I think that to do this, it's going to take time. But in this talk, I hope to present some work that makes progress on reusing data and recycling pre-trained models. And in particular, I'll talk about a question of how we can reuse data across tasks. This will be with not just training a robot on one task, but training a robot on many different tasks and conditioning the robot on a language instruction. And also reusing data through composing different skills to solve a more complex and longer horizon task. And so I'll talk about two projects that try to reuse data across different tasks in order to try to actually generalize zero shot to a new task. And so in particular, rather than just measuring performance, we're really going to focus on measuring generalization to new tasks. And that's the benefit that we should get if we can reuse data and use larger and broader data sets. And then I'll also talk about not just reusing data, but also recycling models. And so we want to be able to develop pre-trained models that we can use for many different possible circumstances, domains, and tasks, and so forth, rather than having to reuse the data set directly and retrain on that data set each time. And so we're going to be looking at whether we can build pre-trained models from in the wild videos of humans that allow us to generalize to an entirely new domain with a new task and a new environment. This won't be zero shot because it's a more challenging form of generalization, but it will require a fairly small amount of data. Cool, so that's a rough outline of what my plan is. First, let's talk about reusing data across tasks. And in particular, we want to allow robots to perform new tasks that they weren't trained to do by leveraging a fairly broad data source, and specifically by leveraging data from a fairly large and broad collection of tasks. Now, it's worth mentioning that there's some previous work on trying to generalize to new tasks. For example, there's some work that does kind of a one-shot generalization kind of approach where you train the robot to be able to generalize from a video of a human doing the task. And this work showed that you can generalize to new objects, but all of it is trained and tested within a single skill, such as placing. And we hope to be able to actually train a model that can generalize to new tasks across a wide range of skills. And likewise, there's also work on language conditioned imitation learning that tries to imitate demonstrations conditioned on a language instruction. And these prior works have shown generalization to new instructions, but they haven't fundamentally shown generalization to tasks that were never seen in the data. And so our goal is to try to allow robots to perform new tasks that weren't in the data, that they weren't trained to do. And so specifically what I mean by this is, say we want the robot to place the grapes in the ceramic bowl, where the robot is going to be in a scene like this. We're going to give it an instruction like this. And the robot will have never seen a trajectory that picks up the grapes and puts it in the ceramic bowl. It will have seen placing other objects into the ceramic bowl and doing other things with grapes, like grasping the grapes and placing them into the tray, for example, but it will never have seen any trajectory of moving the grapes into the ceramic bowl. To make things even harder, we're actually only going to collect data within 2 distinct object sets. So we're going to collect data demonstrations with these objects, collect a separate set of demonstrations with these objects, and we're going to also test generalization of performing tasks with 2 objects that were never seen in the same scene before. Okay, so that's exactly what I mean by generalization. Now, how exactly are we going to do this? We're going to consider a set of 100 total tasks that cover 9 underlying motor skills. And the data collection will look something like this. So here are demonstrations that are collected with the robot with teleoperation. And we're collecting data for 100 tasks. So here are 12 of the tasks. And for each task, we're going to store the language instruction. And this isn't going, we're just going to store a single language instruction per task. It's not going to be natural language in this case. It's just going to be kind of a these words like right here. So nothing super fancy, nothing super complex. We're going to collect demonstrations using an algorithm called HG-Dagger, which instead of just collecting demonstrations of the task, we're also going to record demonstrations from states that the policy reached. And the way this works is you train a policy on an initial set of demonstrations, and then you start running that policy. Inevitably, the initial policy doesn't do well and it gets stuck in some state, and then you collect a demonstration from that state. And then lastly, we also collect human videos doing each of the 100 tasks. And this will allow us not just to perform tasks based on the language instruction, but also to be able to perform tasks by watching a video of a human do the task. And this could be useful in cases where it's easier to actually show the robot what to do rather than to describe it in text. Cool. Kiana, do you have a question?
Yes, so just to get a sense of what the data set looks like. How did you come up with tasks? Like, how did you choose what are the tasks that you're going to collect the data for? And when you say collect many demos, how many, like roughly, how many are we talking about? I want to see like how big is this data set that you're training on?
Yeah, so it's a pretty big data set. The data set has, I think it's on the order of, thousands of demonstrations per task. So quite large, and it might be on the order of hundreds, but it actually varies based on the task. Some tasks have more demonstrations than others, but it's pretty large. And then in terms of how we specified these tasks, initially we actually defined a set of tasks, a set of 21 tasks, just by writing down things that we knew the robot could do from the first object set. And then we knew we wanted to expand the data set. And so we actually then created like a little grammar of like, these are the skills that it could do, these are the objects that it could do it with. And so I think that this set of 12 tasks is fairly representative of the tasks. So it includes things like wiping, placing, picking and placing objects, just grasping objects, knocking over objects, dragging objects. And the total number of kind of underlying skills here is 7. And so there isn't that much variety in the underlying skills, but it's not just like, it's not only pick and place, for example.
I see. So the tasks can be are automatically generated, but they make sense. Like it won't be wipe apple and tray, for example.
Oh, we do have some tasks that don't really make sense. I think that we have something that says like wipe the tray with a banana or something. Okay. And the robot can actually, I think that most of the training tasks made sense, and I think that maybe some of the evaluation tasks didn't make sense. But we'll see a full list of the evaluation tasks when we get to the results.
I see. Thank you.
Cool. And so once we have this data set of 100 different tasks, then we're going to train a policy on this data set. And we're going to train the policy to output the actions of the robot. And in particular, this policy is going to operate on RGB images, and it's going to output 7-degree freedom positions. So this includes the position, the orientation of the end effector of the gripper, as well as kind of an open close command. And this is going to be at 10 Hertz. And so we're collecting all the demonstrations at 10 Hertz. And so then 10 times every second, it gets an image and predicts a command. And then this policy is also going to be conditioned on a description of the task. And that description can either be a video of the task or a language, the language command that we collected. Now, one thing that we found pretty helpful is we found it difficult to train end-to-end from video because that leads to a somewhat weak supervision signal for actually learning representations of these videos. And so what we did is we actually, we trained the video encoder to actually regress to a pre-trained language embedding. And then for the language embedding, we actually don't learn any language embeddings with respect to control. We actually just use a pre-trained model and use the embeddings from that pre-trained model and feed those embeddings into the policy. And we found this to actually work better than just trying to train everything end to end with respect to the video and the language. Great. And then cool. So I guess that's all of what policy works. It's actually pretty simple. We're just training this policy and on all 100 tasks. And then in order to generalize to a new task, this means that the robot needs to correctly interpret either the video or the language command, visually identify the relevant objects. And so, as you might notice, a lot of these images are fairly cluttered. And so it needs to actually figure out within the network which objects are relevant, which objects aren't relevant. And then, of course, translate the perception and the instruction into the action space of the robot. And it's going to be doing this all within a single policy. Cool.
What do you use for the visual embedding? You don't have any like off-the-shelf detector or anything? This is just
so for the encoder of the current image, we don't use any sort of pre-training there. I think we tried ImageNet pre-training and it wasn't really helpful. We do use, to condition on the language in the video, we use film within the encoder of the architecture, which we found, I think, to be helpful. But yeah, we don't do any pre-training on the image itself.
Interesting.
Cool. So then this gets the results. So we trained it on 100 tasks, and we wanted to see if it could generalize zero shot to these new tasks, like the task that I mentioned of picking the grapes up and putting it into the ceramic bowl. And here's a video of the policy. This is shown in real time, and so I'm not speeding it up. I'm not doing anything to make the results look better. And yeah, we see that the robot can figure out that it should pick up the grapes, figure out that it should drop it into the bowl, and successfully complete the task. And what's pretty cool is that it can do not just this task, but you can give it instructions for other tasks as well. And so we can tell it to pick up the banana and place it on the sponge. We can tell it to place the bottle into the tray or to push the purple bowl across the table. And the robot can, sorry, the videos are a little bit choppy, but the robot can, in each of these three cases, successfully figure out how to solve the task and complete it successfully. Ruspa?
A quick question. So does the policy take care of the amount of force that needs to be applied? I mean, for example, for grape, it should not like apply a high amount of force, but for bottle, it's fine to do that.
Yeah, it's a good question. We aren't using any sort of force control. We're just doing the position, so the robot can't control the force. You can imagine using torque control instead. In these cases, I think that all the fruit are plastic, and so we don't need to worry too much about breaking them or anything. But in principle, you could also apply the framework. You could collect demonstrations with an interface that allows you to control the force and the torque.
Yeah, thanks.
Yeah, Kunal?
So yeah, just a quick follow-up question. So in the slide previous to this one, you showed an example where like it picked up the grapes and it exactly put it in the ceramic bowl. Is this because like you had specific ceramic bowl examples in your training set, or like is it able to understand that the green bowl is the ceramic one and the red bowl is, let's say, not non-ceramic?
Yeah, so it had seen these bowls before in the training set, and so that did allow it to figure out which bowl is the correct one. And so really here, we're not necessarily showing generalization to new objects, we're purely showing generalization to new behaviors that weren't in the data.
Got it. Thanks.
Cool. So now let's actually quantitatively look at the results. So we evaluated performance on 28 held out tasks And these were pre-selected and pre-selected tasks that tasks that basically weren't in the training set. This is the full list of tasks. The first 4 tasks are tasks that were collected within a single object set. And then all of these other tasks were tasks that were actually involve 2 objects that are across object sets that weren't seen during training. And then I will show, this is showing the language condition performance. I'll focus on the language condition performance just for the sake of time. And so kind of unpacking this a little bit, we see that on 20 out of the 28 holdout tasks, we see non-zero performance, which is exciting because it means that we are seeing kind of zero-shot generalization in some cases. We also see an average success rate of 32% across all of these 28 tasks. And so this means that there's really substantial signs of zero-shot task generalization, and also considerable room for improvement. And so, yeah, I think that the results are both exciting in that we're actually seeing some generalization to things that it was never trained on, but also there's a pretty big range between 32 and 100. And then before I go to questions, we also asked, like, where is this room for improvement? Like, what would it take to go from 32 to 100? And so to do this, we looked at a little bit of an ablation between different kinds of settings. And in particular, the 32% is held out tasks using language instructions. We also evaluated training performance, basically performance on training tasks conditioned on language and performance on training tasks conditioned just on a one-hot vector of one-hot representation of the task. And what we see is there is an 8% gap between training tasks and held out tasks in interpreting the held out language and performing the held out behavior. And there's a 2% gap between language and one-hot, and then a 58% gap between like just training task performance with a one-hot representation and 100% success. And so what this suggests is that like fine-grained control is really the bottleneck here, not actually generalization to new tasks. Cool. Rose, do you have a question?
Yeah, I was wondering if there were any particular interesting patterns in the failure modes of the held out tasks versus the in-sample tasks.
Yeah, I'll show some videos of held out tasks on the slide after this one. The short answer is that it actually can, on some of these settings where it actually achieves 0% success, it actually does quite well, but we'll see it in the video.
Great, thanks.
Kiana?
This is quite an amazing result. Since you are doing basically the detection of the object, the grasping, learning the policy, learning the correspondence of the language and the actions. I'm very surprised that this is working this well, but a relatively small network as far as I understood. What do you think makes this a big success?
I think that, we're giving it 100 tasks and we're giving it data from lots of tasks. So I think that that's pretty important. I also think that using a pre-trained language embedding was very helpful as well. And when we tried, I think it was like, well, of course, if you condition on a one-hot vector, it's not going to generalize at all. And so like, if we evaluated like held out one-hot, that would be 0%. And so using language is really important. I also think that using a pre-trained language embedding is important, although we didn't do a really thorough evaluation of not using a pre-trained language embedding. And I guess there's like, well, I'll also show that HG Dagger is also really helpful for performance. I'll show that on another slide as well. Yeah, but I think that a lot of it goes into the neural network. The neural network, I think, it's a ResNet. I don't know which one exactly. It's by reinforcement learning standards, it's not tiny, but obviously it's not as big as some of the really massive models we see today. And actually, going back to your question about like, are all of these like real tasks, normal tasks? We do have tasks like wipe table service with a banana, which doesn't exactly make sense, which is kind of cool that it could actually do that some of the time. Tanmay?
Hi, so the question I had was, in what sense are these novel tasks? Is it because, for example, the pick and wipe skill was not seen during training, or is it that pick and wipe skill wasn't seen for that particular instance of tray and sponge?
Yeah, so it has seen these underlying skills, and it has seen doing things with the white sponge, doing things with the purple bowl. It's just never seen a trajectory of picking up the white sponge and putting it into the purple bowl, for example.
Novel combinations of instances.
Yeah, exactly. And also novel combinations of objects as well. For all the tasks underneath this line right here, it never saw a behavior doing things with that pair of objects.
Good, thanks.
Cool, so let's dig into it a little bit more. So for the failure cases, here are two failure cases. The first one, the goal is to pick up the banana and place it in the ceramic cup. And this was a skill, or this was a task that got a 0% success rate quantitatively. And what we see is that it figures out that it can pick up the banana, and it clearly knows that it should go to the ceramic cup. But then just when it actually places into the ceramic cup, it can't quite actually get it correctly into the ceramic cup. And so at the final state, it hasn't succeeded. And it's just kind of this very last part of the task that is not quite succeeding. And then for the case of wiping a tray with a sponge, we also see that it's able to figure out that it should pick up the sponge correctly. And it also moves towards the tray successfully, even lowers the object into the tray, and it just can't quite actually start wiping the tray with the sponge. And so this suggests that it understands, it seems like that what, I mean, I don't necessarily want to use the word understand, but it seems like the network has figured out maybe like actually even like 95% of the task, but it just can't quite finish the last part of the task in some of these cases. In other cases, we do see some failure cases with like grasping, for example, but overall, I think that in most of the cases, most of the failure modes, it seems like the network kind of knows what to do. It just can't quite, perform the fine-grained control in order to successfully solve the task. Cool. And then the last comparison that we looked at is, I mentioned that we collected data with HG Dagger or human gated Dagger. And what this is showing is we trained a policy only with expert demonstrations. We trained another policy with half expert demonstrations and half of these intervention data with HG Dagger. And this comparison is controlling for the total amount of data. And we see that the policy is much more successful, has a 53% success when we train with HG Dagger, whereas it only has a 27% success rate if you don't train with HG Dagger. And so this suggests that having that intervention data is really, really critical for basically combating the compounding errors that you see arise in imitation learning. Cool. And then the last thing that I'll mention is that all of these results were with like a synthetic language. They weren't with kind of natural language commands. And in a separate project, we were also looking at kind of learning language conditioned behavior. And in this project, in all of our simulation experiments, we also trained with a scripted language because we didn't want to collect natural language data. And what we found is actually just by nature of using a pre-trained language model, we were actually able to generalize to some degree for free with to natural language just by nature of using a pre-trained model. And so in particular, this is the success rate of this method, of the method they were doing only trained on scripted data and using a pre-trained model. And this is the performance in this column is showing performance only trained on scripted data without a pre-trained model. And what we see is that when we actually give it instructions of unseen verbs, unseen nouns, unseen verbs and nouns, and unseen natural language, we see that the performance does drop. It goes from 56% to like 51% or 46%, but it actually can still somewhat generalize to these new kinds of instructions. And without the pre-trained model, you don't generalize nearly as well. And so the performance drop is like closer to 20% rather than 10%. And so this suggests that actually pre-trained language models trained on like just language data can actually allow you to generalize somewhat nicely to natural language. Cool. So the takeaway here is that we are able to get zero-shot task generalization to new tasks with language conditioned imitation learning. And I'll also mention that all of the data, all of the robot data is publicly available, and we're hoping that that will allow people to use the data and also study this kind of problem. Cool. So I'll move on to the next part, which is instead of just trying to perform new tasks that use kind of new combinations of objects, we want to be able to perform new long horizon tasks. And this might mean that we not just need to like generalize to new combinations of objects, but also new combinations of skills. And there's a very common hierarchical framework for doing this, which is to learn some set of skills and then plan over those skills to solve long horizon problems. And so we're going to use the same kind of framework, but we're really going to focus on this first part of the problem, of actually learning the options or the skills. And in particular, if we're going to learn options or skills and try to generalize in a compositional way, we first need a library of multiple skills, of course. We also need preconditions and postconditions for each of these skills. This is really important for being able to plan over those skills. And lastly, we need these skills to be reliable enough that if we sequence them together, the performance actually is still reasonable. If you kind of put together skills that have a success rate of like 30%, for example, then once you try to sequence those skills, chances are you probably won't have any success rate once you sequence a few of those skills. Cool. And it actually turns out that I think that a lot of imitation learning and reinforcement learning algorithms don't actually consider necessarily all of these aspects of the problem. And so we're going to try to design an algorithm for learning these kinds of skills that achieve these desiderata and allow us to actually plan over them to solve long horizon problems. And in this case, instead of using imitation learning, we're going to use reinforcement learning because this should allow us to learn skills, ideally learn skills with a higher success rate. And we're going to use a model-based reinforcement learning algorithm that learns a latent representation and learns a dynamics model, an action condition dynamics model in that latent representation. And this will be trained with respect to the latent representation of the future image. This model can be trained on data across all of the skills. And so we're going to be training kind of this VAE and this latent dynamics model across all of the data that we collect. And then we're separately going to train a reward classifier that classifies between human examples, like kind of positive examples of completing a skill, and negative examples of completing a skill. These negative examples will come from the robot's experience. And this reward function will be used for Q-learning, kind of a standard Q-learning algorithm that will be done in the latent space of our variational autoencoder. And the classifier and the Q function will both be trained on skill-specific data because they're somewhat specific to each skill. And so first, by sharing data for when training this model in the VAE, this should lead to more efficient learning. And this makes it more practical to learn an entire library of skills rather than just one skill. These reward classifiers, rather than only using them as a reward function for Q-learning, we can also use them for helping determine the pre and post conditions of each skill. This is important for providing the grounding for planning. And then lastly, we will actually replan with respect to the model and the Q function at test time. So whenever we're in a new state, we can actually use the model, look ahead, also evaluate our Q function, and actually update the action that we would take. And this should actually provide greater robustness to a variety of states, because if you reach a state that you weren't expecting, then you could replan according to your dynamics model and your Q function. Question?
Yes, so when you collect the positive and negative examples, how do you make sure your negative examples are good are hard negative examples? And because if it's too easy, probably the model can overfit or can easily find the can easily classify the bad ones from good ones. But how do you make sure that these are like good negatives?
Yeah, so this is a really great question. So all the positives come from humans. For the negatives, we actually use, when we were running reinforcement learning for learning the Q function, we actually use all of the robot's experience as negatives. And this actually means that first, it'll be really hard negatives because the robot is actually trying to optimize against this classifier. And second, it also means that some of these examples will actually be true positives. Now, the way that you can actually get around this is if you balance the positives and negatives in a batch. This means that at the very least, true positives will get a value of a classifier probability of 0.5. And so this is kind of the sort of technique of using the robot's experience as negatives is a technique called vice or variational inverse control with events. It's also very similar to things like Gale, except it's just on observations. And it allows you to get hard negatives. And by balancing batches, it allows you to kind of avoid the problem of these kind of noisy negatives, or some of them are actually positives.
Nice, thanks.
Cool. So we use this approach to learn skills. So it's kind of a model-based RL approach that learns both a model, a Q function, and these reward classifiers. We use this to learn a repertoire of 14 different skills. These skills include things like opening a cabinet, closing a drawer, inserting a marker into a holder, and grasping an object on a desk. And then we specify pre and post conditions for all of these 14 different skills using image classifiers. Some of these image classifiers will be exactly the ones that we were using for reinforcement learning. We also need to learn a few additional image classifiers because the reward functions don't cover the entire space of pre and post conditions, especially for preconditions. We can reuse some of them for preconditions, but for the other ones, we have to actually train a new image classifier. And then lastly, once we have the pre and post conditions and the skills, we can actually just use an off-the-shelf symbolic planner to actually sequence these skills. You can also do something much more sophisticated here. You could actually learn a higher level policy over these skills. But because we're focusing on this first part, we're just going to use an existing planner and kind of leave more sophisticated things for future work. Cool. So we evaluated this on long horizon tasks, all with image observations. In this case, it will all be with novel objects. And first, I'll show some qualitative results of the long horizon tasks. On this, in the left case, the goal is to put the three objects on the table into the cabinet. And here's a video of the robot performing the task. And so we see that it doesn't always succeed immediately at grasping an object, but it has to retry sometimes, but that allows it, by retrying and replanning, it actually is able to figure out how to kind of eventually grasp the object. In this case, it needs to kind of pick up all the markers and put it into the marker holder. And then in the last case, it needs to, we're trying to kind of leverage all of the skills, and it basically needs to kind of rearrange each of the three objects into the drawers and the cabinet. Cool. And then quantitatively, we evaluated, we were really comparing kind of different approaches for learning these underlying skills. And we looked at this algorithm, the model-based algorithm that I mentioned, and we compared it to not using a model and only learning the VAE and the Q function. We compared it to not using the model or the VAE. And this is similar to an algorithm called QT-opt. And then lastly, we compared it to not using the Q function and only using the model for planning. And this is similar to an algorithm called B. And what we found is, first, in terms of the success rate on the low-level skills, we see that first, the Q function is really important for low-level skill performance. So we see like a 30% improvement in skill performance. We see that if we drop the model, the performance only drops a little bit. If we drop both the model and the VAE, the performance drops a little bit more. But these numbers are still fairly respectable. And then when we look at actually success rate on the long horizon tasks, we see that there's kind of, in general, all the numbers go down because these tasks are a lot harder. But because the skills from the model-based algorithm are pretty reliable, this drops less than when we drop the model versus if we drop both the model and the VAE. And so essentially, by replanning with the model, we get better reliability or robustness of these skills, and that's really important for long horizon performance. Cool. So the takeaway here is that multitask model-based RL provides skills that support long horizon activities. And kind of overall, you showed that we can generalize to new tasks with new combinations of objects and tasks with new combinations of skills. Now I want to talk about not just reusing data, but also like trying to pre-train models, like models that can be recycled for new domains and tasks. And so instead of just reusing data across tasks, we're actually going to be reusing a model, a pre-trained model in these new scenarios. And so as motivation, kind of as we sort of talked about a little bit, the typical robot learning paradigm is to consider a task that you want to do, like folding this towel, collect a bunch of data for it, train a policy, and then deploy that policy. Of course, this is really inefficient and expensive because we're collecting the data from scratch for each task. And what we want to be able to do instead is, instead of just reusing a previous data set from other tasks, we want to be able to download a pre-trained representation and just build on top of that representation. So we want to be able to then collect a few demonstrations of the task and then train a policy on top of that pre-trained representation, and ultimately then deploy the policy with the representation. Okay, so no, it's worth mentioning that there's actually a number of works that try to do pre-training for control. The first class of works often do use self-supervised learning objectives, but they typically do self-supervised learning on the target domain. And I think that this has some merit, but the downside is that I guess a lot of the scenarios where we've seen like a lot of success from self-supervised learning is when you do pre-training on a really diverse set of out-of-domain data. And then there's a second class of work that uses out-of-domain data like ImageNet, but it uses data sets and objectives that are really designed for image categorization and less designed for control. And so what we'd like to be able to do is figure out a data set and objective that allows us to pre-train representations that are particularly well suited for vision-based robotic manipulation. And so what we're going to do is instead of using like static images from like ImageNet, for example, we're going to use video data of people doing things. And this will be pretty diverse data from all over the world. That is, yeah, of people doing lots of different tasks in lots of different environments. And instead of training for like a categorization-like objective, we're going to try to incorporate temporal information into the representation, also incorporate semantics and parts of the image that are semantically relevant to the task. And lastly, some form of sparsity objective that tries to allow us to get a more compact representation to enable efficient downstream learning. And so specifically what we're going to do is we're going to use the Ego4D dataset, which is a new dataset that was released from Facebook that has all these videos of humans as well as language descriptions of what the human is doing. We're then going to use this to first going to perform time contrastive learning on these videos to pull together frames that are close in time and push apart frames that are far in time. We're also going to try to align the language description with the video, also with a kind of contrastive approach where we bring together language description of that video and push apart a language description that isn't of that video. And lastly, we'll use an L1 penalty to encourage a more compact representation. And then once we perform this training on this pre-trained on this data set, we'll take this representation and use it as as an encoder for efficient imitation learning in new environments and new tasks. And so we'll look at learning both on a real robot as well as in a few simulated domains. To dive a little bit more into the details of how this works, the L1 penalty on the representation is pretty simple. Specifically for time contrastive learning, we're going to use a contrastive objective to pull together images that are close in time and push apart images that are far in time and images from other videos. And then in terms of language alignment, we're going to also use a contrastive objective. And instead of just trying to predict the language command, for example, we're going to try to train the representation such that if you have another model on top of the language command and the representation, you're able to predict whether or not the language corresponds to that video or not. So essentially, this should allow the representation to encode things like the language. Okay, so now that we have this pre-trained representation trained on these videos and trying to incorporate things that we think are relevant to manipulation, we're going to first evaluate if this enables efficient imitation learning on unseen environments and tasks. Then we're going to evaluate which components are important and understand how performance varies across viewpoints and demos. And then lastly, we'll look at whether it enables efficient learning on a robot. Cool. And so in terms of our evaluation, we're going to look at low data imitation learning from pixels. And what I mean by low data is we're going to give it around 5 to 25 demonstrations of the downstream tasks, so a pretty small amount of data. And we're going to train a MLP policy on top of the fixed representation. So we're not actually even going to fine tune the representation. We're just going to train a policy on top of it. We're going to look at 3 different simulation domains, the 5 tasks from Meta World, 5 tasks from this Franka Kitchen domain, and 2 tasks from this dexterous manipulation setting. We're also going to look at not just kind of one viewpoint from each of these environments, but actually 3 different viewpoints from these tasks to try to also just make sure that the representation doesn't just work for one viewpoint, but actually lots of different kinds of viewpoints. Okay, so we're evaluating how well the representation allows us to fine tune on all of these different tasks and these different viewpoints. So this performance is going to be averaged across tasks and viewpoints. And I'll show performance not just of R3M, but also of supervised ImageNet representations, self-supervised ImageNet representations, and clip representations. And I'll also show performance from scratch. So first, here's the performance of learning from scratch. It gets around a 30% success rate, which isn't very high, understandably, because it's a pretty small amount of data. Next, we see that these pre-trained representations improve over learning from scratch by a little over 10%. And so this means that they're using pre-trained representations is helpful in these settings. And then lastly, we see that using R3M, we actually see a 10% improvement over these prior approaches. And so specifically, we see a 10% improvement in success rate over clip, MoCo, and supervised ImageNet features. And we see a 20% improvement over learning from scratch, which is pretty large. And so this suggests that using videos rather than static images and using these kinds of temporal, objectives that use temporal information and language information are helpful for learning representations that are specifically for manipulation rather than for image categorization. We also did an ablation on different components of using data augmentation, using an L1 penalty, and using the language component. And we see that removing crop augmentations and removing the L1 penalty only slightly hurts performance. And the L1 penalty is actually most helpful for the Franka Kitchen and the Meta World domains. It's actually a little bit, it actually hurts a little bit for Adroit. But the kind of most significant difference that we see is if we remove the language alignment loss. We see kind of an 8% difference in, an 8% drop in performance. We see this especially on the Adroit tasks. That said, when we remove the language component, this actually still is doing better than the prior pre-trained representations. Cool. And then we evaluated performance across different viewpoints as well. There isn't too much interesting here, but I guess one thing that's a little bit interesting is that for different viewpoints, we do actually see differences in performance for prior methods. Like Clip does well on view 2 and view 3 of Meta World, but actually does not quite as well on view 1. But R3M is kind of consistently improving performance across all 3 viewpoints. And then lastly, if we give it varying amounts of demonstrations, we see that absolute performance increases with more demonstrations, as we would expect. And the performance improvement that we see from R3M is fairly consistent across these different numbers of data, these different numbers of demonstrations. Great. And then most importantly, we looked at actually efficient learning in the real world. And so these are experiments that we collected 20 demonstrations. This takes less than 10 minutes to do. And here's what the results look like. So one of the tasks is to put lettuce in a pan. And after collecting 20 demonstrations and training a policy, we get a policy that looks like this. that's able to kind of successfully pick up the lettuce from different positions and put it into the pan. We also give it 20 demonstrations of closing a drawer in this environment, and it can successfully close the drawer. We also tried it on the folding towel task that I mentioned before. And lastly, also pushing a mug to a goal position. And overall, we see that if we evaluate performance using the pre-trained representation versus using clip features, we see that R3M actually almost doubles the performance of using clip features in these environments. And we only consider clip here just because running evaluations in the real world is a little bit more expensive than in simulation. Cool. So the takeaway here is that R3M can be used off the shelf for data efficient manipulation. We also tried to make it really easy to allow other people to try it out. And so once you kind of install the repo, it just takes 3 lines of code to be able to evaluate the representations from the model. Yeah, so I hope that this is kind of a step not just towards reusing data, but also towards reusing models in robotic manipulation. So I guess to summarize a little bit, I talked both about reusing data and reusing models. In the first part of the talk, I talked about how we can generalize zero-shot to new tasks with language conditioned imitation learning and to new long horizon tasks by using a kind of a multitask model-based RL approach. And lastly, how we can generalize to entirely new domains, entirely new environments with a small amount of data by pre-training representations on videos of humans. I'd like to also briefly mention a few open questions that I think are really important. I talked a lot about reusing data, and in the projects that I mentioned, we were reusing data across tasks rather than using data from a specific task. But I think we really need to take this a step further and reuse data sets from entirely previous projects rather than other tasks. We've started to do this in some of our own work. And so we had one paper that kind of took a data set from a previous paper, used offline reinforcement learning to train a policy on that data set. But I think that there's a lot more work to be done to allow us to start reusing data sets for every single project rather than just for some of the projects that we do. And second, in the last part of the talk, I talked about how we could pre-train our state representation for control. And I think that in the context of embodied learning, we should probably be pre-training a lot more than just a state representation, because the actions and trajectories that a robot takes is also a big part of the problem, not just perception. And so we could imagine potentially pre-training a goal condition Q function, which we've looked into a little bit. We could try to pre-train a dynamics model. And we've also looked at trying to pre-train dynamics models from videos of humans. But I think that this is like a pretty wide open question. And if we can pre-train more than a state representation, we should be able to get, they should be much more powerful than just a pre-trained state representation. Cool. With that, I'd like to thank my students and collaborators. I should mention that Eric and Alex led the first work that I presented. Bohan, in collaboration with Suraj, led the second work that I discussed, and then Suraj led the third project that I discussed. Yeah, and happy to take some more questions.
Thank you so much for the great talk and really interesting results. So I think the point you make about reusing the data and how computer vision community has ImageNet and robotics community is lacking that. I resonate with that a lot. But one question that I've always had is, how would you reuse the data that is collected for a different embodiment? So for example, you might have robots that can only navigate, or how would you do it for for the robots that can manipulate, but they have different arm kinematics? How can we actually reuse the data that we've collected from the past projects?
Yeah, I think that's a great question. And I think it's something that is important for us to figure out. I don't think that we know the answer entirely, although I think that, I mean, in some ways, in this last work, we were actually using data from a different embodiment. We're using videos of humans, and we were able to see significant gains from using that data. And so I think that there's a lot of rich information in that data across embodiments about how objects interact with each other, how physics works, what the world looks like and everything. And so it certainly seems like we should be able to use it. I think that we may need to learn kind of adapters that kind of adapt between different action spaces. Maybe we need to try to convert action spaces into a common form. Like if these robots, maybe they have different kinematics, but maybe we're always controlling the end effector in 3D space in like centimeters or something like that. And so I think there should be ways to combine them. I also think that fortunately neural networks can figure out a lot of things. And so if you have a lot of unlabeled data, then the neural network could figure out that like if you give it a Franca robot versus a Sawyer robot or something, that it needs to change the representation in a certain way. So I'm optimistic about that. I think it gets even harder when you have completely different sensors, like an RGB image versus some robots might have tactile data. We've actually been working a little bit with audio data recently. But I also think that neural networks are really flexible, and we've been seeing architectures come out that can deal with all sorts of data modalities and so forth. So in some sense, I think we should just force the model to figure it out. Although if there are things that we can do to make it easier, like putting everything into centimeters or something, then we should help out the networks a little bit in that sense.
Thank you. Yeah, this is definitely a very interesting direction. Do we have any questions from the audience? Okay, then. Thank you so much, Chelsea. And this was a really interesting talk, and we hope to see you soon in conferences and hear more about the continuation of these works. Yeah, thank you everyone for joining, and see you all.
Thanks for having me, and thanks for the great questions in the middle.
Yeah, thank you. Thank you so much. Bye.